Welcome to this presentation of another case study dealing with cracking of alloy pigtails made of 800H austenitic stainless steel as a reducer in a fertilizer plant. These reducers are made of nickel-based alloy and they are used. What you see in the picture is the pigtail which connects the reformer tube, large diameter reformer tube, to a small diameter pigtail. So the syngas comes here and gets reformed and then goes for further operation through this pigtail. These reformer tubes are centrifugally cast with high diameter and high thickness, whereas the pigtail is made of wrought tube, and these pigtails, so small diameter pigtail and the large diameter centrifugally cast pipe, are connected through a reducer. Here is the reducer, and you can see it is reducing from the large diameter to a small diameter, and this has been giving the problem prematurely. It is a high temperature equipment, so that hot gases they attack, they lead to oxidation, and also because of size reduction there is a stresses developed, and reducers are under high duty of mechanical forces and also thermal forces. In a fertilizer plant, after some very short period of running, these reducers started cracking, and so that is why this study was made in detail. So what you see here is the typical austenitic microstructure of the 800H, which is a nickel-based alloy with austenitic microstructure, and this is the typical acceptable structure. What we call it step structure, austenitic step structure. You can see annealing twins and slip bands, and this is an acceptable structure. This is also taken from one of the reducers which is being used. On the other hand, the failed reducers show a differential microstructure. As you see here, the outside is coarse grained, and then inside is gradually reducing the grain size, and the finer grain size, seeing the gases on the inside. This is the gas flowing on here, and this is the outside hot gases which are used for heating the tubes, are here on the gas outside. You can show this differential microstructure is not acceptable, and that is why it is mentioned here, not acceptable across the wall of a failed reducer. Wall is only about maybe 3 or 4 mm thickness, and that there is a due to gradation in the microstructure, cracks develop. You can see the crack initiating on the inside, where hot gas is coming inside, and then the cracks develop. This you can see porosity. This is a porosity, and cracks of developing due to heating and cooling towards the outside surface. Cracks develop on the inside surface. They propagate to the outside surface, resulting in leaking. And this is the typical failed reducer. So here is a comparison of the acceptable microstructure and the non-acceptable microstructure going from outside surface to the inside surface. And this has not cracked, whereas this has cracked in a very premature period. And you can see the reason is the microstructure difference. Here is a comparison of the test-made microstructural and other tests made between the unfailed and the failed reducers. The middle column is unfailed reducers, and the right column is failed reducers. You can see the chemical analysis also. Chemical analysis, there is a variation in the impurities here. Here is the unfailed reducer, it conforms to specification, whereas the failed reducers, particularly the crack forming impurities like sulfur, lead and tin, they are very much higher than the maximum limit specified. And this is the same for all other properties. The ferrite content here it is satisfactory, whereas here it is very high compared to 0.8% on the unfailed new tubes, whereas here it is a failed cast tube. The ferrite content varies from inside to outside. Unacceptable microstructure, ferrite content. Similarly, magnetic characteristic. Say, Incolloy 800H is a non-magnetic austenitic stainless steel variety, hence it is non-magnetic. Whereas the failed one is a magnetic, and this itself shows there is a lot of ferrite content due to the compositional variations, and the the observation on the inside surface smooth and free from any foreign material. That is so far as the unfailed one. Whereas the failed one, thick greenish black carburized layer to about 50% wall thickness. The carburization leads to brittleness and very easy to crack. So here is the hardness variation. You can see about 165 VHN, and it is uniform and acceptable. Whereas here hardness unacceptably high as compared to 165. Here we are seeing a gradation of 190 to 397. Both are very higher than this value. Hence, since hardness is a range and unacceptably high, the brittle fracture can easily take place due to some temperature load variation. So the summary microstructure is unacceptable for unfailed one, and it is a typical austenitic, the so-called stepped microstructure, whereas it is a non-acceptable microstructure in the failed ones. The non-acceptable gradation of structure, cast structure in the outside surface, and carburization on the inside surface. Because due to casting, there is a preferential carburization on these defective reducers. So soundness, this is a sound throughout, like localized blowholes present, hence sound is defective. So this is the comparison. So the diagnosis, the failure is due to the usage of cast structure with inherent casting defects instead of forged structure. So this is the diagnosis, and apparently there is a mixing of cast and forged roots in the supplies made. So a recommendation for remedial measures: ensure that the reducer is made from forging instead of casting. Forging gives more information, more uniform microstructure as compared to casting. Since the microstructure is uniform and sound, cracking does not take place in the forged ones. Thank you for listening to this case study.